The learning objectives of this chapter are that the learner will know the requirements for a basic fuel system for a diesel engine, know the various components in a diesel engine fuel system, know the basic principles of operation of the components of the diesel engine fuel system. The purpose of the diesel engine fuel system is to deliver the correct amount of fuel at the correct time to the correct cylinder in the required condition at all engine loads. The system must therefore be equipped to control the quantity, the timing, the period, and the sequence of delivery. There must also be control functions which ensure that the fuel is in the correct condition and that the delivery is suited to the actual load. Systems vary greatly, ranging from the most basic mechanical hydraulic types to those using load-dependent electronic controls for quantity and timing adjustment and distribution to individual cylinders. No matter how simple or sophisticated the system is, the basic requirements must be met. In this chapter, we will look at the basic system and consider some of the common alternatives to the basic components and control functions. Fuel is drawn from the service tank by either gravity or by an electrically driven or engine-driven supply pump, and delivered to the high-pressure fuel pump inlet rail. For residual fuels, it is necessary to heat the fuel after it leaves the service tank to ensure correct injection viscosity. In a basic direct fuel injection system, the high-pressure pump usually delivers fuel directly to the fuel injection valves. The force resulting from the hydraulic pressure within the fuel injection valve causes the valve to open and fuel to be admitted directly into the cylinder combustion chamber. As we will see later, the high-pressure fuel pump can be used to control the quantity of fuel entering the engine cylinder, and along with the fuel injection valve setting, can be used to control the timing of the fuel delivery. The main components within any diesel engine fuel system are usually considered to be the high-pressure fuel pump and the fuel injection valve. The features of these two components can provide timing and quantity control, as can the pump driving mechanism. The driving mechanism is often a cam mounted on the engine camshaft. The camshaft is normally driven by the engine crankshaft. Some recent engines are designed without a camshaft and use electronic control for fuel timing and quantity. Where residual fuels are used, the fuel system requires a heating system with a viscosity control function. To prevent gassing, the heated fuel is normally delivered pressurized to the high-pressure fuel pump suction rail. An input from the engine governor is usually used to give the load signal for any changes in fuel timing and quantity during engine operation. We will look briefly at engine governors in a later section. The majority of high-pressure fuel pumps used on diesel engines are of the jerk type. The term jerk relates to the sudden sharp movement of the pump plunger during fuel delivery. This ensures a very rapid, almost instant, fuel pressure rise in the supply to the fuel injection valve. To achieve this type of motion requires that the pumps are driven by cams rather than cranks. The profile of the fuel cam can be shaped to produce the desired delivery rate from the pump. We will look at fuel cams in more detail later in this chapter. On larger diesel engines, the high-pressure pumps are usually single units positioned close to the cylinder cover for the unit they are supplying. This means that the high-pressure fuel pipe lengths can be kept to a minimum. The pumps are actuated by the main camshaft. For smaller engines, inline multi-cylinder pump blocks are often used. These blocks house all of the high-pressure pump cylinders for the entire engine. A single control rack serves all of the fuel pump plungers. A small sub-camshaft is used and placed within the pump housing. To ensure that piping losses are similar, some engines have the pump block positioned close to the middle of the engine with equal length high-pressure pipes to each fuel injection valve. There are a number of different methods used by which the quantity and timing of delivery can be controlled for a high-pressure fuel pump. The most common method is to use a helical profile machined into the pump plunger element, which controls the start of injection and the spill point by covering and uncovering the suction and spill ports in the pump barrel. Depending on how the helix is positioned, either the start or end of injection, or both, can be varied. Some variations are shown here, with constant start and variable end, variable start and constant end, and finally, variable start and end. The last of these is a form of variable injection timing, which we will look at in more detail later. The other common method is to use suction and spill valves to control the start and end of delivery instead of having a helix cut into the plunger. The term spill is used to define the point at which delivery ends and fuel is spilled back to the pump suction or return line. With both of these methods of control, distribution of the fuel to the different cylinders is achieved by having an individual pump element for each cylinder unit of the engine. Click on the buttons to learn more about the different types of control. The sketch shows a simple representation of a cam-operated, helix-controlled, high-pressure fuel pump. The cam lift is transmitted to the pump plunger through the cam follower. The pump plunger, which sits inside a barrel in the pump housing, has a helical profile machined into it. The barrel has suction and spill ports cut into it and a slot for the locating pin. The lower part of the plunger is provided with a machined flat section, which fits into a slotted sleeve with a toothed collar. A control rack connected to the governor engages with the collar of the slotted sleeve to give control of fuel quantity delivered. The pump housing is provided with a suction and discharge connection. A delivery valve is housed in the discharge connection. Let's see how the pump works. The sketch shows a simple representation of a cam-operated, valve-controlled, high-pressure fuel pump. The cam lift is transmitted to the pump plunger through the cam follower. The pump plunger, which sits inside the pump housing, is plain, with no profile machined into it. The lower part of the plunger has a collar, which carries two valve operating levers, which pivot on eccentric shafts. The eccentric shafts are positioned in such a way that as the plunger moves up, the levers actuate the suction and spill valves. The position of the eccentric for the suction valve actuating lever is preset, so that the start of injection is constant. The eccentric for the spill valve is connected to the output from the engine governor and is arranged to give later opening of the spill valve, and therefore increased fuel delivery as the engine load is increased. The pump housing is provided with a suction, spill and discharge connection. A delivery valve is housed in the discharge connection. Let's see how the pumps work. In addition to the two main methods described previously, there are also other ways in which control can be achieved. Some recent engine designs have introduced electronically controlled fuel injection systems. With this type of system, constant delivery pumps are used to deliver high-pressure fuel to a manifold, which is often referred to as a common rail. The common rail supplies fuel to each cylinder via electronically controlled timing valves, which control the admission of high-pressure fuel to the injection valves. We will look at this system again later. Some engines use distributor-type fuel pumps. Unlike the previously described control methods, this type of fuel pump controls not only the timing and quantity delivered, but also to which cylinder unit the fuel is delivered. It is more likely to be used on smaller engines. To see the principle of how a distributor-type pump works, click on the button. Distributor-type pumps are self-contained quantity, timing and distribution units for the supply of high-pressure fuel to a diesel engine. A pump unit consists of a cam ring inside of a pump housing. The cam ring has machined cam grooves, one for each engine cylinder. A set of cam rollers are positioned within the cam ring and turn with the rotor. The cam rollers act on a pair of pump plungers, causing them to move radially in and out as the rotor turns. The rotor is part of the drive shaft and extends into the distributor head. It has two radial drillings, an inlet and outlet, which connect to a central axial drilling. The distributor head has a single inlet connection and an outlet connection for each cylinder fuel injector. When the rollers are sat in the cam ring grooves, the fuel inlet connection is aligned with the inlet drilling in the rotor, and the fuel pushes the pump plungers outwards, filling the space between them. As the rotor turns, the rollers rotate out of the grooves, forcing the plungers inward and delivering high-pressure fuel to whichever delivery connection is aligned with the outlet drilling in the rotor. The inlet connection and inlet drilling line up again, and the plungers are again forced out as the rollers enter the cam ring grooves. The example used for the animation is designed for a single-cylinder engine. It can be shown that the thermal efficiency of the diesel engine is related to the ratio of the maximum cylinder pressure, Pmax, and the compression pressure, Pcomp. Generally, the higher this ratio, the greater the efficiency and the lower the specific fuel consumption will be. With fixed fuel injection timing, the value of Pmax varies with the load as a linear or straight line characteristic. The maximum value of Pmax is limited by the strength of the combustion chamber components, whereas the minimum value for Pcomp is limited by the need to achieve sufficient compression temperature to ignite the fuel. By altering the timing of the fuel injection, we can alter the value of Pmax. Advancing the fuel injection timing will normally increase the value of Pmax, and retarding will normally reduce it. If we advance the fuel timing as the load reduces, the value of Pmax can be maintained at the maximum value, although this is only practical over part of the load range. By doing this, the ratio Pmax-Pcomp, and therefore the thermal efficiency, is increased over that part of the load range and specific fuel consumption is reduced. In simple terms, this is why variable injection timing has been developed and introduced. Click on the buttons to see how VIT can be achieved with the different pump control methods. From what we have already said about helix control, you will hopefully realize that if the vertical position of the spill port relative to the leading edge of the pump plunger is altered, then the point at which injection starts will be changed. Raising the spill port relative to the plunger will retard the injection timing, and lowering it will advance the injection timing. This change in relative position can be achieved by either raising or lowering the pump barrel or the plunger. Let's see how variable injection timing can be achieved using a pump with helix control. As the timing rack moves to the right, the pump barrel will be raised up a small amount. This moves the spill port away from the leading edge, and injection will start later. Now, if the timing rack is moved to the left, the barrel will move down, and injection will start earlier. If this change is done in response to load changes, then the injection timing can be adjusted in such a way that maximum value of Pmax is maintained over part of the load range, therefore increasing the efficiency. The most common fuel pump faults We have said that opening of the spill valve is used to vary the end of injection on valve control type high-pressure fuel pumps, with later opening increasing the delivered fuel quantity. For VIT control of this type of pump, we also need to vary the point at which the suction valve closes. Earlier closing advances the injection timing, and later closing retards the timing. Let's see how variable injection timing can be achieved using a pump with valve control. As the governor output lever moves in response to a change in engine load, the linkage moves to rotate the suction and spill valve eccentrics. This causes the valve levers to move closer to or further away from the valves. This alters both the start and end of injection, giving variable injection timing throughout the load range. The geometry of the linkage is designed so that the suction valve closes earlier or later depending on the actual engine load. The spill valve opens later as the load increases. Altering the position of the eccentrics in response to load change allows the injection timing to be altered so that the maximum value of Pmax is maintained over part of the load range, therefore increasing the efficiency and reducing specific fuel consumption. There are a number of other ways that VIT can be achieved other than altering valve timing or repositioning the barrel. This usually requires adjustment to the cam follower position or the camshaft. If the cam follower is connected to a pivoted horizontal lever carried on an eccentric shaft, then rotating the shaft will cause the follower to move horizontally, relative to the vertical center line of the fuel pump and cam. This will cause the pump plunger height to vary relative to the rest of the pump, resulting in varied injection timing. Another method used to achieve VIT is to have the camshaft drive arranged as a sliding helical spline coupling with an axial servo motor. As the servo motor operates, it causes the coupling to slide along the spline, and because of the helical form, this causes the camshaft to rotate relative to the drive, so altering the timing. In both of these arrangements, the timing adjustment is made in response to load change. The most common fuel pump faults are internal and external leakage resulting from erosion of pump elements and valve seats, and damage caused by fuel contaminants. Severe internal or external leakage can affect the timing and the quantity of fuel delivered to the cylinder. This can be caused by general wear or by cavitation erosion. Cavitation erosion occurs when a sudden pressure drop causes vapor bubbles to form, which then collapse, resulting in excessive impact forces as the liquid fills the vapor space. Erosion can occur due to the high flow speeds across control edges and valve seats. Abrasive and corrosive damage may occur due to fuel contaminants. Overheating of the pump elements due to either high temperature or low lubricity of the fuel can cause plungers to stick, or, in extreme cases, seizure may occur. Some engines are provided with fuel pump lubrication facilities to prevent this occurring. Fuel pump maintenance is limited due to the extremely fine clearances of the operating parts, and is usually restricted to replacement of seals, valves, and pump element. Adjustment is usually limited to the pump timing and initial setting of VIT mechanisms. Checking of the pump timing and the adjustment methods used vary depending on the actual pump type. Some of the more common methods of checking the pump timing are given in the list. The majority of the fuel pumps used for fuel injection are cam-driven positive displacement types. The rate at which fuel is delivered to the engine cylinders is dependent on the engine speed and the operating profile of the fuel cam. The fuel cam shape is made up of a number of sections. These are the base circle, the peak, sometimes referred to as the dwell, the rising flank, and the falling flank. Most fuel cams for reversible engines have identical rising and falling flanks. The fuel pump plunger will be stationary when the cam follower is on the base circle and the peak of the cam, and moving when it is on the flanks. We can think of the rising flank of the cam as the operating profile, with three separate parts: the acceleration, the controlled speed, and the deceleration sections. It is the controlled speed section of the cam profile that governs the rate of fuel delivery. Fuel pump cams can either be separate components or an integral part of the camshaft. Only those which are separate components can be adjusted individually. Some manufacturers use split cams to make replacement of damaged cams easier. Although there are still a number of engines which use bolt-on or spline-mounted cams, the majority use hydraulic tapered sleeve couplings, often referred to as muff couplings, to mount the cams on the camshaft. A tapered sleeve with a threaded end fits onto the shaft, and the cam, which has an internal tapered bore to match the sleeve, is mounted on it. A lock nut holds the assembly in place. The cam is provided with an oil hole, which passes from the outer surface to the inner bore. This is normally blanked off with a screwed plug. Let's see how a fuel pump cam with a hydraulic tapered sleeve coupling is adjusted. When the cam needs to be adjusted, the lock nut is first slackened back and the screwed plug is removed from the oil hole. An oil pump is connected to the oil hole, and hydraulic oil is pumped through the connection and enters between the cam body and the outer surface of the tapered sleeve. A vent is normally provided to clear the air from the oil hole. The high-pressure oil compresses the sleeve and expands the bore of the cam, which causes the surfaces to separate slightly. By applying a force through a suitable arrangement, the cam can now be moved circumferentially to a new position relative to the camshaft and sleeve. The lock nut is now run up to the cam and the oil pressure released. As the pressure falls, the cam contracts and the sleeve expands, giving full contact between the surfaces. The cam is now in a new position and the fuel pump timing has been altered. The purpose of the fuel injection valve is to admit fuel into the cylinder and to act as a non-return valve to prevent air and combustion gas from the cylinder passing back into the fuel system. Although there are many different designs of fuel injector, most are similar and work on the same principle. The valve consists of a body and a fuel nozzle, which houses a needle valve. The needle valve is given positive seating by the injector spring through a thrust piece. The needle valve lift pressure can be changed by adjusting the spring compression screw. As fuel pressure acting on the needle valve increases, the generated hydraulic force overcomes the spring force, and the needle valve lifts off the seat, allowing fuel to flow to the injector nozzle and through the nozzle holes into the cylinder. The pressure drop across the nozzle hole accelerates the fuel, and the high-velocity fuel stream breaks up into fine droplets as it passes through the high-pressure dense air. As soon as the pressure in the fuel injector drops, the needle valve reseats due to the spring force, and injection ends. With a standard type of fuel injection valve, fuel only flows through the valve when the valve is open. When operating on hot, heavy fuel oil, there is a risk that the fuel will cool down sufficiently so that the high viscosity of the cold fuel will block the injector. To minimize this risk, it was common practice to change over to diesel fuel before stopping the engine. Many fuel injectors are now designed to have the fuel recirculating continuously when the injector is closed. Click on the button to learn more about recirculation types. For the valve shown, recirculation is achieved by having a slide valve inside of the main needle valve. When the fuel pressure in the valve is at normal supply pressure, the main needle valve and the slide valve are seated. The recirculation port is open and fuel flows through the valve body. The most common faults found with modern fuel injection valves are as indicated: damaged or fouled needle valve seating surfaces, leading to dribble or leakage; scored or burnt needle valve and housing, which may lead to seizure or internal leakage; damaged or blocked nozzle holes; breakage or weakening of injector spring; leakage at mating surfaces; carbon deposits due to overheating. For the majority of modern fuel injectors, maintenance consists of periodic testing in a test rig. Any fault found in the operation is normally corrected by general cleaning, replacement of the needle valve and nozzle assemblies, replacement of the injector spring, or exchange of the complete injection valve. Some injection valves may have renewable seals, and some may require reconditioning of mating surfaces. Some of the recirculation types have service exchange cartridges, consisting of the needle valve and slide valve and the thrust assembly. These types usually have separate nozzle tips which can be changed if damaged. You should always refer to manufacturer's instructions and only use approved replacement parts and assemblies. One of the greatest hazards when operating a diesel engine is the risk of a high-pressure fuel leak spraying fuel mist onto the hot engine surfaces, resulting in a potentially serious fire. To minimize this risk, many engine manufacturers use double-skinned pipes to protect against this. For engines over 250 mm bore operating in unattended machinery spaces, this is a class and SOLAS requirement. The inner pipe is usually a solid drawn steel pipe, and the outer skin is usually a flexible metal sheath with a drain provision. The drain is led to a collecting pot, usually with a leakage alarm. Some systems include a cutout for the high-pressure fuel pump for the affected unit. As an alternative to this arrangement, some smaller engines have all of the high-pressure pipes contained within a steel enclosure, which drains to an alarmed collection pot. Most marine diesel engines operate with direct injection, which, as the name implies, are those in which the fuel is admitted directly into the engine cylinder, as opposed to those where the fuel is pre-mixed with the combustion air in a pre-combustion chamber. We have already described the hydraulically controlled type when we looked at a basic fuel injection system. The other type of system is referred to as a common rail system. In this type of system, high-pressure fuel is delivered to an accumulator, the common rail, which is connected to each fuel injection valve by an electronically controlled timing valve. The common rail fuel pressure is maintained at a constant high pressure, usually above 1000 bar. The engine management system passes signals to the electronic timing valves to admit the correct quantity of fuel at the optimum point in the cycle to the fuel injection valves. The injection valve then operates as a normal hydraulically operated valve, with the fuel pressure providing the lift force. The engine management system can have various inputs in addition to engine load and speed. Many systems are set up to give optimum fuel efficiency with acceptable levels of exhaust emissions. The control of a diesel engine fuel system is achieved using a fuel regulator, which is commonly called a governor. We will not go into any detail in this module, but we should consider the different types commonly used. There are 3 types to consider: mechanical hydraulic, electro-hydraulic, and all-electric. The basic principle of a governor is the same, irrespective of the type. A measured value is compared to a set or desired value, usually either engine speed or load. The resulting difference is then used to alter the governor output to either increase or decrease the fueling rate to the engine to bring the engine speed or load, or both, back to the desired value. In many cases, the governor also acts as the engine overspeed preventer and may be part of the overspeed trip facility. Of equal importance to the correct quantity and timing of fuel injection is the condition of the fuel as it enters the diesel engine cylinder. If the condition is not right, then poor combustion will result, even if the other 2 conditions are correct. Once the fuel has been correctly cleaned of contaminants, the critical concern is to ensure that the viscosity is right to achieve good atomization. Although heating up the fuel will reduce the viscosity, there is so much variation in fuel content that operating with a fixed temperature is insufficient. This means that there is a need for automatic viscosity control. Click on the button to see how viscosity control can be achieved. Viscosity can be thought of as the resistance of a fluid to flow, and this fact is used to measure and control the viscosity of diesel engine fuel with a viscotherm. As the fuel flows through the viscotherm unit, part of the flow is pumped through a capillary tube. This creates a pressure differential along the length of the capillary tube. This pressure differential will increase as the viscosity increases. A differential pressure cell is connected across the capillary tube, and the output from the cell is used as the input to a control circuit, where it is compared to the set value for the viscosity. The output from the control circuit is used to operate an automatic steam valve. If the viscosity rises, then the increased differential pressure causes the steam valve to open further. You should by now realize that the critical parameters for a fuel injection system operating on heavy fuel oil are the fuel temperature and viscosity. We can also include the supply pressure to the high-pressure pump inlet manifold as a critical parameter. This pressure should be high enough to prevent vapor formation in the hot fuel. Low pressure in supply to the high-pressure pump manifold can result in engine operating problems. The high-pressure fuel pumps may get starved of fuel, particularly at high engine loads. Vapor may form in the hot fuel supply, causing the system to gas up, resulting in loss of fuel to the engine. As a minimum, therefore, the following alarms are usually found in the system: fuel temperature high and low, fuel viscosity high and low, and fuel surcharge pressure low. You should always make yourself familiar with the features and alarms of any of the onboard systems that you sail with. If we consider the preparations that are required just for the fuel system when starting an engine from cold, for example after an overhaul, the following steps are required. All fuel tank and system valves should be correctly set. The distillate fuel pump should be started. The system should be checked for any leakage. All fuel pumps and injectors should be bled through to remove any air. The system should be checked again for any leakage. When all other engine warming through procedures and preparatory checks are completed, the engine is ready to be started. Once the engine is running, and assuming heating facility is available, preparations can be made to change over to heavy fuel. When changing over from diesel fuel to heavy fuel oil, some mixing of the two fuels will occur. Care must be taken not to overheat the fuel mixture, as this may result in gassing up of the system if the diesel fuel gets too hot. It is usual to manually control the heating during initial stages of the process before changing over to automatic viscosity control. After setting the valves and starting the heavy fuel oil pump, the temperature of the heavy fuel oil is gradually raised to about 80 degrees Celsius by circulating it through the heater. Once at this temperature, the changeover valves are put into the heavy fuel position, closing off the diesel fuel supply to the fuel system. As more heavy fuel oil enters the system, the viscosity will start to increase from the low viscosity of the diesel fuel. Once the viscosity reaches the normal set value for heavy fuel operation, the heating is increased manually to maintain it at that value. As the fuel temperature approaches the expected value for heavy fuel operation, the viscosity control can be changed over to automatic. When changing over from heavy fuel to diesel fuel operation, care must be taken not to overheat the diesel oil or undercool the heavy fuel, and a similar procedure to the above applied in reverse should be adopted. Depending on the engine type, these procedures may take up to 2 hours to complete. You should always follow the manufacturer's specific instructions for a particular engine type. Click on the button to learn more about Recent changes to MARPOL Annex 6 and the introduction of C-cars has brought with it the problem of compliance regarding the sulfur limits of fuel in use at the time of entry into a C-car. It is a requirement that the sulfur content of the fuel in use at the time of entry into a C-car is no more than 1.5% mass by mass. For a ship normally operating on high sulfur fuel with a limit of 4.5% mass by mass, this means that prior to entry, most of the fuel in the system has to be replaced by low sulfur fuel to bring the total sulfur content in the system to less than 1.5% mass by mass. The time taken to complete this changeover can vary from a few hours to a number of days, depending on the amount of fuel in the system and whether or not the vessel is equipped with separate settling tanks and service tanks for high and low sulfur fuel. A changeover calculator provided by Lloyd's Register is shown here. The example illustrated is for a vessel with single settling and service tanks and a system capacity of 2 tons, giving a total fuel quantity of 22 tons at the time changeover to low sulfur fuel is started. At a consumption rate of 2 tons per hour, and for the sulfur levels indicated, the calculator estimates a total changeover time of 27.5 hours. This takes into account the fact that the dilution of the sulfur content will be a gradual process as the fuel is consumed, with the ratio of low sulfur fuel increasing over time. You should realize from the example just described that if the vessel had separate settling and storage tanks for each fuel grade, then the quantity of fuel to be diluted would only be that in the system, and the changeover time would be much shorter. Whenever the engine fuel system is to be shut down, the system should be left with diesel oil in it whenever possible. This will require that the changeover from heavy fuel to diesel fuel is timed to ensure that all the heavy fuel in the system is used up before the engine is stopped and the system shut down. The changeover procedures, similar to those already discussed, should be adopted. All of the operational procedures for startup, shutdown and changeover should be included in the ship safety manual as part of the ISM system. In this chapter, we have considered in some detail the requirements for a diesel engine fuel system. We have considered the various types of high-pressure pumps that are in use and the methods used for timing and quantity control. We have considered the standard fuel injection valve and looked at some variations, such as those with recirculation. We have also considered the other usual elements of the fuel injection system, including viscosity control and system alarms. Finally, we have looked at preparing the system for operation, including various changeover requirements. Try the questions in the following self-test to check your understanding so far.